Okay, so we'll just do some problems related to time response and its specifications. So I'll start with a fairly simple looking problem. So is to find the step response of the system. So I have a reference which is a unit step, S plus 4, and this is a 1 here, and this is my y of s. Okay. So there could be two ways to do this, right? One is by applying the formula for y of t. And if you remember, this essentially was based on omega n and zeta. Okay. So, okay, first let us see how the closed loop looks like. The closed loop transfer function here, y of s over r of s is 25 say s square plus 4s plus 25, and this is of the form omega n square over s square plus 2 zeta omega n s plus omega n square, right. So, therefore, I can easily compute omega n is 5 and 2 zeta omega n is 4, and therefore, zeta can be easily computed to be s 0.4, and this will be radians per second. Okay, right, and then you can clearly see that this is an underdamped response or an underdamped system. Okay, and I know that the response looks like this. Y of t is 1 minus e power minus zeta omega n t over square root 1 minus zeta square sine omega dt plus cos inverse zeta, which I had termed this as theta in my earlier classes, right. Okay, and then once I know, so I know the zeta, I know the omega n, I could compute omega d as omega n square root 1 minus zeta square, which turns out to be 4.58 radians per second, and I do all the computations and I just end up with this expression 1 minus sorry. Right, I will just skip the intermediate step, but it should be easy to compute it this way. Okay. Another way to do it, that I know y of s is 25 s square plus 4s plus 25 times 1 of s, and I could just write this down in this way. Okay, and so this would be 1 the inverse Laplace transform y of t would be the inverse Laplace of y of s, and okay, this would be 1, this would be e power minus 2t over cos okay, and this is equal to this. Okay, so I could compute directly by the formula or using the inverse Laplace transform, right, based on whichever is comfortable. Okay, so the next problem I am given g of s is 25 over s plus 5, h of s is 1, and I have a negative feedback. Okay. Now, here I have to find out what is omega n, zeta, omega d, rise time, percentage overshoot, and settling time. Okay, so the transfer function of y of s to r of s is gs over 1 plus g h, that would be okay, 25 over s square plus 5s plus 25. Okay. So, I just compare this with the general form of omega n square plus s square plus 2 zeta omega n s plus omega n square. It gives me omega n is 5 and 2 zeta omega n, this is 2 zeta omega n is 5, and therefore zeta is 0.5. Okay, so I know omega n, I know zeta, I know omega d is omega n square root 1 minus zeta square, and that will be 4.33 radians per second, and I have the rise time computed as pi minus theta over omega d, and theta was defined as cos inverse zeta over omega d, and this is okay, 0.48 seconds. Okay. The peak time, we computed this as pi over omega d. So, omega d is over here, and that will just be 0.725 seconds. Okay. And then the percentage overshoot was directly depending on the damping, that was given by e power minus pi zeta 1 minus square multiplied by 100 to get the percentage, and I could compute this as 16.36%. And finally, the settling time for the 2% tolerance criterion, okay, it's just 1.6 seconds, right. And quite straightforward, right. Once you write down the closed loop and compute what is omega n and zeta, then everything else just fits into the formula, right. Okay, the third problem is, well, I'm given a system like this, 10 over s plus 2 4 over s plus 8 plus a minus this. Okay, this is a 1, this is my y of s. And the problem is to find the steady state error for a unit step input. Okay. If I had done this 3 or 4 lectures ago, I would have done, used calculated first the transfer function y of s, r of s is 40 over g over 1 plus gh, that would be s plus 2, s plus 8 plus 40 over s square plus 10s plus 56. Okay. So 2 weeks ago I would just do this, right? So it's 40 over s square plus 10s plus 56, and then I would do okay, so y of s over r of s. This is my transfer function. And then I would compute what is the final value. I am not really interested in finding the entire signal with time, but I am only interested in finding the steady state error. So, what is the final value of y? So, from the final value, so, the final value says limit s going to 0, s times y of s for a step input. This would be limit s tending to 0, s times y of s. So, y of s, sorry, this should just go away, right. So, y of s would be 40 over s square plus 10 over plus 56. So, I will have 40 over s square plus 10 s plus 56, and this would be 40 over 56, which is 0.714. Okay. And the steady state error is the actual signal r of t or the actual reference minus the actual output. So, there is 1 minus 0.714 is 0.286, 0.286. Okay. But since, okay, this is a slightly longer process, but now I know directly how to calculate the steady state error given the type of the system, right. So, I have, if I look at this, this was called the G of s, it is a type 0 system and I am tracking a unit step, and I know that there will be some position error, of course this tells me already that. So, how would I compute that? Okay. So, ESS was 1 over 1 plus Kp, right. This was for a type 0 system with a step input. Okay. And then Kp was limit s going to 0 g of s, right. So, that was, what is g of s? So, this guy 40, so g of s is this one, right. So, g of s, I am just looking at the open loop transfer function, is 10 over s plus 2 I have s plus 8 and I have a 4 here. Okay. So, limit s going to 0, g of s was 40 by 16 is 2.5. Okay. So, this is my Kp. So, the steady state error is 1 over 1 plus Kp is 1 over 1 plus 2.5, and that can be easily computed to be 0.286. Right. So, the advantage here is I do not really need to compute the closed loop transfer function. I can just look at the loop transfer function or the open loop transfer function and then compute these things directly. Okay. So, again this is they lead to the same thing, not surprising. Okay. So, in the last problem, so I am given a system which looks like this: R of s, E of s, I have a gain k, I have a certain disturbance, and then I have a plant which looks like this: 1 over s times h, where h is any number or any integer value. I have s plus 2 over s plus 1 s square plus 10s plus 40, right. This, so this is my entire plant as it looks, and a negative feedback as usual, a plus here, a minus here, just a 1 here. Okay. So, this is my t of s, this is my k, and so on, and this is my y. Okay. So, in the first part, I would want to find h such that for suitable values of this gain k. Additionally, let me assume that the disturbance is identically equal to 0. So, the h should be such that the steady state error for step reference or step input is 0, and the steady state error again for a ramp reference is a non-zero constant. Okay. Which means we are just interested in finding the type of the system. Okay. So, let us recollect quickly. So, if I have a type 0 system and the input being a step, my ESS was 1 over 1 plus Kp. Okay. This was again for h equal to 0, right. So, this step input is what I am looking at, that the steady state error for a step reference is 0. Okay. Now, when h equal to 0, I would have some steady state error, this is not 0. So, I should at least have h to be 1, h to be 1. So, that I have a type 1 system and then a step input, then ESS goes to 0, okay, that we know. Now, is that the answer? Well, if just this was the statement, I could say that h could be 1 or even more, h could also be 2. H could be 2 and this statement would still be satisfied, that the steady state error would be 0 for type 1, type 2, type 3 and so on. Okay. However, the second statement says that in addition to the steady state error for a step input to be 0, it should also have a non-zero constant error for a ramp input or for a velocity input. Okay. So, what was the nature of this thing? So, if I have a type 1 system, okay, and the input is a ramp. Okay. So, I know that a type 0 system will not be able to track a ramp and the error is infinity, and h is equal to 0 is ruled out anyways, right. I will start with h equal to 1. Type 1 system, a ramp input, I know that there is a constant error. Right, given by I think 1 over kV or something like that. Again, we know how to compute that kV. Okay. So, the answer would be that h, well, it of course cannot be 0, it can be 1 or greater because of the second statement, and the third statement restrict it only to be 1, because if I have a type 2 system, then the error is not a non-zero constant, it will go to 0, right. Or type 2, if I have a type 2 system and a ramp input, my ESS goes to 0, right. So, this is not allowed. So, I am just at type 1 system, and therefore, the answer is h should be equal to 1. Okay. Okay. So, in the second part we will do something little more interesting. Okay. So, let me call this block as G prime of S, and the second part what I want to find a k such that when this disturbance signal dt is a step and the reference RT equal to 0, okay, then I want to find, okay, so the limit t going to infinity y of t should be equal to 0.01, right. So, I want to find a gain k such that when there is no reference and a disturbance which is a step, that y of t should go to 0.01. Okay. Now, after this, for this value of k, find the steady state error for unit ramp and dt equal to 0, right. Okay. So, let us do the first part until here. Find a k which under a step disturbance and no input will give me an output at steady state at 0.01. Okay. So, this my y of s over d of s when r is 0 takes this form is g prime of s d of s plus 1 plus k g prime of s, and we saw how to derive this transfer function in the previous tutorial. Okay. So, now what I would want is d of s is a step, right. So, y of s is 1 over s, which is my step disturbance, and I have s plus 2, s plus 1, s square plus 10s plus 40 plus k s plus 2, right. So, this entire thing here expands to this one, okay, the straightforward computation. Now, y at infinity is again I apply the final value theorem, s 0 s times y of s, and I do all the math and I get this is 2 over 2k, right. So, 2 and everything else will disappear, and this y at infinity should be equal to 0.01, right. So, the question was find a gain k which for d being a unit step results in a steady state y of 0.01. So, I just solve this and I get that the value of k is 100. Okay. Now, in the second part, okay, assume there is no disturbance, I take this value of k to be 100. Okay. I will also do this was the first part. So, I am not even interested in what is the value of h at the moment. So, for this, so this 100 was computed. Okay. So, we did use so h will actually be equal to 1, right. We keep the value of h from the previous one and then compute the value of the gain k such that the output is 0.01, and that k was computed to be 100. So, I know what is the h now, I also know what is the k. Okay. So, for these two values of h and k, I want to find the steady state error for a unit ramp and assuming dt equal to 0. So, this is again a type 1 system. Right. And I have a input which is a unit ramp, and I know that the error is definitely not equal to 0 and it is some constant value. So, let us compute what is that constant value. So, the steady state error is 1 over kV, or kV is the velocity error constant. And what was kV? kV was limit s going to 0 s times g of s, okay, I can do all the math, limit s going to 0 s times, so I will take this entire g now. This would be s times k is 100, in the numerator I have s plus 2, denominator h equal to 1, so I have one pole at the origin, s plus 1, s square plus 10s plus 40. Okay. So, okay, so I can do all the computations. So, this guy goes away, in the numerator I am left with 200 and in the denominator I am left with 40. So, this is my kV, right, this is 5, and ESS therefore is 1 over kV and that is 0.2. Okay, it is just straightforward using the formulas. The only trick is to how to get this transfer function from d to y, putting r equal to 0, finding the appropriate value of h, and then finding k again by using the final value theorem, and then using just the formulas for steady state error given that the system is type 1 and the input is a unit ramp. Yeah. Sorry? This is just y of s. Oh, sorry. Okay, d of s will go away. So, okay, or I will just do this one. Right. This is y of s over d of s is, so there will be no d here. Okay, and that d will be taken care of here. And all this we assume here that that the r is 0. Right. Okay. Thank you.